exhibit allotropy, we call them allotropes of that element. So you say allotropes of carbon, allotropes of sulfur. With allotropes, we're not even dealing with the mass number or the atomic number. Here, they have the same chemical properties. Allotropes have the same chemical properties, so you're not interfering, nothing interferes with their chemical properties with allotropes. However, they exist in different physical forms, and such they have different physical properties. Because they exist in different physical forms, they have different physical properties. However, their chemical properties are the same. So nothing changes in terms of their chemical properties with allotropes. There are so many examples of allotropy as well, and it is actually possible for an element to exhibit both isotopy and allotropy. A good example of that is actually carbon. Carbon exhibits both allotropy and isotopy. So for crystalline carbon, the isotopes of carbon include diamond and graphite, and these have different physical properties. Diamond is very hard, while graphite is very soft. Another example is sulfur. So I've highlighted two allotropes of sulfur. In fact, you can interconvert rhombic sulfur to monoclinic sulfur by just playing around with the temperature. If you subject rhombic sulfur to temperatures between 96 to 119 degrees, it gets converted to monoclinic sulfur. If you cool monoclinic sulfur below 90 degrees, you get back your rhombic sulfur. So they just exist in different physical states, but in terms of chemical properties and chemical behavior, it's still the same properties that they share. I hope you find this helpful. Please like, follow, and share. And I hope you find this helpful. Please like, follow, and share, and subscribe. You can check out the playlist on the other definitions. Um, if you like me to define any term, leave it in the comment section, and I will do that next time. Thank you.